Atomic radius, as you may have learned before, typically refer to the distance between the center of the nucleus and its outermost orbit. However, in some covalently bond molecules, the atomic radius is equivalent to the covalent radius, which is calculated by halving the distance between the two atoms. Across a period, the atomic or covalent radius decreases. Take elements in period 3 as an example. There is a clear decreasing trend from sodium to argon. This is due to the increase of protons, which makes the attraction of the nucleus stronger. At the same time, since the number of principal quantum shells did not increase, the shielding effect from the inner shells stays relatively constant, resulting in a decreasing trend. The ions of elements follow a very different trend. The cations have a much smaller radius than the original atom. This is because they gave all their valence electrons away, which meant that they lost their outer shells. Without the repulsive forces between the outer shell and the inner shells, the shielding effect weakens. With the nuclear force unchanged, the atomic radius decreases. From the graph, we can conclude that the more electrons the ion lost, the smaller is its ionic radii. The anions, opposite to the cations, have a larger radius than their atom form. This is because the ion gained more electrons, and resultantly, the outer shield has a larger repulsive force which increases the shielding effect. From the graph, with chlorine minus having the smallest and phosphorus 3 minus having the largest radii amongst nonmetals, the radii increase as the charge decrease. We will next look at some more macroscopic properties. The metal-metalloid boiling point decreases in order from silicon to sodium, and the nonmetals decrease from sulfur to argon by their molecule size. The boiling point of metals increase from left to right as atoms towards the right can form more positively charged ions and a bigger sea of delocalized electrons, which gives the atoms a stronger metallic bond. Silicon does not have a metallic structure, but it naturally forms a giant covalent structure. The strong covalent bonds are difficult to break, which gives it a high melting point. The nonmetals have a lower melting point due to the weak van der Waals force between the molecules. Their melting point depends greatly on the size of their molecules, as it is positively correlated to the strength of the van der Waals force. Next is reactivity. The reactivity of metals-metalloids decrease in order from sodium to silicon, and the nonmetals increase in order from phosphorus to chlorine. It is clear that the reactivity decreases amongst the metals since the ionization energy increases across the period. Take the reaction with water as an example. Sodium reacts violently with cold water, whilst magnesium only reacts with steam. Nonmetals have an increasing reactivity across the period due to the increase of electronegativity. In summary, the more edges the element in a period, the more reactive it is. Next, we will look at oxidation number. Here are all the oxides of period 3, and apart from sulfur dioxide with an exception of +4, the oxidation number increase across the period. The first two metal oxides are always basic. Aluminium is a bit special, being amphoteric, and starting from silicon to chlorine, all their oxides are acidic, and acidity increases across the period. The chlorides formed by elements are also something important to remember. Here are all the chlorides of elements in period 3. The first two metal chlorides are ionically bonded and neutral in pH. This makes them ionic lattices that are soluble in water. The rest 3 chlorides are all covalently bonded. They are acidic in nature because they hydrolyze in water, making an acidic solution and fuming hydrochloric acid. This is all for this video. Thank you for watching and subscribe for more A-level chemistry videos.